And we are live. Hello, good evening, Singapore, and welcome to the first Data Engineering Singapore meetup. It's our first of the year and also the last for the year. and um, Today we have two speakers. My name is Dick Chun. I have a co-organizer, Ravindra, who will join in a minute. And today we are very happy to have speakers from two companies. One from Confluent, Wei and Anna from Confluent. We'll talk about Kafka clusters and designing disaster recoverable clusters. And we have Donald from Data Spark, who will talk about Apache Airflow. Right. So today's theme is about how to move data and how to use some of these platforms to design proper data movement and handling, right? And okay, um, without further ado, I'll let the speakers introduce a bit about themselves while they before they present. And Jiwei will go first, followed by Donald. There will be a short break in between, and we hope to have questions posted through the YouTube channel, and we'll be able to see them and respond to them at the end of the presentation. Right. So hope to see you. Stay around till the end of today. Right. Before that, maybe I'll just flash a bit of the screen. Hold on. Yeah. Yeah, the screen now you see is from me. We are from Data Engineering Singapore Meetup Group. So this is the first meetup, as we said. Um, we really look forward to nurturing a local network of good data engineers, and because I think we need to get more connected, and it's hard to find also good, competent engineers in this domain. So we hope to connect with one another through this meetup. And we also have other channels from the same meetup group in terms of Discord and stuff. We will broadcast that later in the meetup group. Right up. Without further ado, I will hand over to Jinwei, who will introduce himself and the talk he's going to do today. Right, Jinwei, you want to share your screen first?
Yeah,
Yeah.
sure. Let me share screen and move this out.
Okay. Right. I think we are ready to go. Right. Over to you, Jinwei. I will just show the full screen.
Yeah, sure. Thank you.
All right.
Hey,
Thank
thanks
you.
for taking. Yep. So, just quick introductions, then we'll get started. I'm Junwei with the Confluent Professional Services team. I'm a solutions architect here. So, day to day, what I do in my life is basically consulting in terms of architecture design around Confluent platform, and then also with some deployments and also designing around basically different of the customers' requirements around security, around disaster recovery, right? So that's why we are here today. So this is one of the biggest asks that we get in actually myself in my day-to-day life, right? Is what makes a resilient Kafka cluster, right? Kafka cluster, Confluent Platform cluster. What makes it resilient, and how can I then use this in my organization, right? To so that we are resilient to data center failures, component failures, because these things happen all the time, right? So it's hard to avoid. Lately we had AWS going down again, right? So it seems to from being a once every couple of years or 3 years type of occurrence to almost annually we have situations arise, right, with our infrastructure, right? So how then can we design our platform, right, our Kafka cluster or Confluent platform to then be resilient to those types of disasters, essentially, right? So this is typically what we go through. So I'll try to condense. Usually we spend like days or many sessions to get this through, but we'll try to condense into a few main points, right? So when we talk about disaster recovery, right, primarily what we are interested to is component failure. Component meaning your instance goes down, networking is out, hardware, some server goes down. also have seen before floods, fires, killing data centers and things like that, right? So data centers going down, right? Or AZs if you're on cloud, right? So on the cloud. All right, so these are what we are most interested in. So from a basic Kafka design, so I'm not sure if everybody is familiar with Kafka and how things work, right? So you have your Kafka cluster, you have your producers, which is going to be producing into your clusters. And then you would have your consumers, which are consuming from the topics within your cluster, right? So within this setup, right, there are different configurations for essentially your produce and your cluster. So there's many different ways you can configure your cluster in terms of design, where to place what are the settings to use, things like that, right? So, and we will go through some of the more popular configuration. But first, we'll start with the single data center cluster. All right, so one DC cluster. Even with, let's say you come look for me and you say, I have only one data center, so what can I do to be resilient, right? So there's a couple of ways that you can even do that. So within your Kafka cluster itself, right? Cluster, let me try to draw this. You would have brokers, you would have zookeepers and things like that. So the most common design we have, things happen in threes, right? So we will have three meaning that if you have one broker down, you still have two alive. So that's a pretty robust type of setup, right? And then you would have likewise for zookeepers, right? Zookeeper 1, zookeeper 2, and then zookeeper 3. All right. So this is your standard vanilla Kafka cluster, right? That basically brokers, zookeepers, nothing else, right? So if you're interested, there's other components, things like Kafka Connect. From Confluent platform, there's control center, schema registry, things like that you can also add to your cluster. But this is your plain vanilla one. In fact, we don't have to do trees. What I'm doing like that is you can do a cluster like one broker, one zookeeper, right? But that doesn't give you much resiliency in terms of if one of the components die, then we are basically, we don't have service, basically. Right? I'm trying to choose the less shocking choice of words. Right, so let's go. So producers producing into the cluster. First and foremost, one thing you should note, right? So with Kafka, there's a concept of topics. And with topics, right, there are configurations. Topic configurations, sorry. So partitions, how many partitions, right? Replication factor. And then more importantly, minimum in sync. Let me just type the whole thing. I cannot spell minimum in sync replicas, right? So partitions actually is another one of my most number one asked questions, how many partitions I should have. This really depends on your workload, how many consumers you need to process all the data that you have. So just suffice to say that the higher throughput that you expect and the longer it takes to process each message, the more partitions you require. All right, so we will, because we only have 1 hour, so let's not spend too much time on this. So let's just give it an arbitrary number, let's say 3, right? Replication factor, right, in most cases, this is basically how many copies of the data I want to store within my cluster, right? So if I say replication factor of 1, essentially this data is only copied one time to one of the brokers. And the worry here is that once that broker dies, then you don't have that data, right? So typically for a 3-broker cluster, my recommendation would be a replication factor of 3, right? So later on, we'll run through what the implications of each of these means. So minimum in sync replicas is the more interesting one. And this is something that is often neglected, as well as it goes hand in hand with our producer configuration called X. Right, so if you were pre-Kafka 3.0, right, the default was 1, right? So 2.8 and before, right? This was Kafka 2.8 and before. And then right now it has been changed to all or -1 is the same thing since Kafka 3.0. All right, so that is the important thing to consider. If you are running any clusters now and you were running a before 2.8 cluster, try to check right now whether your producer configurations are configured correctly when it comes to your X. Right, so acknowledgements meaning one thing, right? When I produce a message, M1, my favorite message, right? So M1 will come in, producer says, I want to produce M1. There's 3 possible configurations for X. It can be 0, meaning fire and forget, right? So the producer just says, I produce M1, and the client library takes that M1 and tries to produce into cluster. If there's no connection here, M1 would still succeed because I don't care about acknowledgements. I just fire and forget, right? So even though nothing gets copied into the brokers, M1 is it's gonna just disappear, right? But if you choose X equals to 0, then which nobody ever does, right? So then that means that you are okay to lose data. So I'm just gonna put a minus right through to discourage you from doing that, right? So X equals to 1, meaning I produce this message, right? So we have a concept of leader, brokers, and followers. Later on in the demo, you can see that for a particular topic partition, right? Topic and partition, there is a leader broker and the rest are followers. So meaning one of them would handle all the produce and consume for that specific topic partition. And the rest would be just to store the copies of the data. All right. So what this means is, let's say, for example, broker 1 is the leader of, I'm abbreviating a lot of things, right? Because we kind of don't have a lot of time for this. So, but hopefully you will get an idea of what I'm trying to cover. All right. So you have 1 leader, 2 followers, right? Because replication factor of 3. In total, 1 leader, 2 followers give you 3 brokers, right? So you always produce to the leader broker, right? So there's no way you can produce to a follower, right? This is Kafka. So your message produces gets into broker 1, the leader. Acknowledgements equals to 1 in this case. I have 1 broker that has a copy of that message. I will immediately acknowledge, right? So I already satisfied your requirement. You told me it's acknowledgements of 1. So I'll just acknowledge, I say act. Right, then my producer will then carry on with producing my next favorite message, M2, right? Then while all this is happening, right, meanwhile, right, the follower brokers would periodically poll your leader broker, and then it will get copies of M1 copied to them at their leisure, right? So this is X equals to 1, and this is the default before Kafka 3.0. All right, so this is something to take note of. And another thing I forgot to mention is that from Kafka's perspective, right, we are looking at a smart client and not so smart platform type of a setup, right? So meaning that your clients basically are the ones that say, hey, my configuration is acknowledgements equals to 1. So he tells the broker, the producer would tell the broker knows that, oh, your acknowledgements equals to 1. There's no way I can enforce at the broker side that, hey, I will wait till all of the brokers have your data before I acknowledge back to you, right? So that's a separate setup that requires smart brokers, right? So in Kafka, you will have the brokers are basically built for speed. Right? You just produce bytes into it, doesn't check for anything, just whatever you give me, I will just write it out in bytes. Right? So when you want to read from me back again, I'll just give you everything back in bytes. Right? So it's a byte array, bytes in, bytes out. All right. So this was x equals to 1, right? So slowly. So the issue here is that, there it could happen, right? When brokers 2 and 3 take their, no, I mean, not take their own sweet time, but more like if they are slower or there's a case where, your next message gets produced in or not, right? And at this point in time, to the broker, I have received acknowledgement for M1, so I'm settled. I don't have to care about it anymore, right? To the producer. Then your broker 1 dies, right? So I use the word die a lot, but it's more like fails, right? So there's a failure in this broker. Then what happens is you basically lost your message M1. Let's say it was a disk hardware failure, right? So you lost your message forever, but the producers really don't know that you have lost that message, right? So if you were in, IoT space, right, it's fine. You just lost a sensor data. I mean, nobody is too hurt. Right? But if this was in a banking scenario, for example, then you potentially lost a bunch of transactions that you cannot recover anymore, right? So that's some of the things that you have to take note of, right? So which is why I was extremely excited, right, when the community basically set x equals to all or -1 as the default for your producer client since Kafka 3.0. So what this means, all, right? All doesn't mean all the brokers need to have the copy. All means this: my producer, same scenario, producers M1, broker has that. It depends on this, right? So it means my minimum in sync replicas number of brokers need to have this message before I acknowledge. So typically in this kind of setup, we'll do 3 and 2, right? So if you are more worried, you can do 3. 3 meaning all 3 brokers must have a copy of M1 before I acknowledge to the producers, all right? So if I set to 2, meaning broker has received it, written into my log, I don't acknowledge immediately, right? So I will wait till one of these 2 guys, right? So it could be broker 3, fetches the replica, right? And then copies into their log. And then there's now minimum in sync replicas. There's now 2 in sync replicas, right? In sync meaning I'm up to date, right? So then it satisfies the requirement. Then I will say, okay, act. Right, so this already provides you a single DC cluster, just that one setting, 2 settings actually. Replication factor set, if you set to a reasonable number, you set it to 1, there's nothing we can do, right? So if it's 1, it's 1, and if that one broker dies, we are all in trouble. And min in sync replicas also, if you set it reasonably, 3 and 2 in this case, you are protected against a single broker failure, right? So if one of these dies, right, you're still fine, right? You still have an in-sync replica in broker 3, right? So this will then be promoted to be the new leader, right? And then your producer will then go to produce back into this guy. All the while your M1 is perfectly safe, right? So that's the whole gist of it, right? So this is single DC resiliency. Not much to do with design, but more to do with configurations, right? So just a combination of x equals to all on your producer side and your replication factors and minimum in sync replicas to be set accordingly. All right, so that's the single DC cluster. Then things get a lot more exciting, right? So these things also apply for multiple DC settings. It's just that what I'm showing you is that if you, I mean, not everybody is running multiple DC types of clusters, right? So what I'm saying is that even for a single DC setup, there are choices you can make that will help provide you with some level of resiliency, all right? So for 2 DC clusters, right, things get a lot more exciting, right? So there's many ways of doing this, right? There are folks that are more interested in, the traditional designs, All right, so I'll call this Kafka cluster 1. And let me just nuke all of these to make it cleaner. So same thing. So x equals to all, right? So if there's nothing you have gained from today, it is set x equals to all. That's explicitly. Right? So that will help with a lot of trouble down the road. Right? So we have seen folks who lost data, and is being in a bad situation because of setting x equals to 1 or just taking the default. All right, so let's go with that. 2 DC clusters, right? Straightforward. I have 2 clusters now. So what do I do with them, right? So the most common, right? Common, not as in I recommend it, but the most common as in the domain, right? Folks in the industry are familiar with this pattern, right? This will be the active passive and the active active, right? So these are the 2 more commonly seen design patterns. So what this means is you will have 2 separate clusters. So I'm familiar, everybody is familiar with that. I have 2 SQL databases, right? Then I can run one as active, one as primary, secondary, whichever you want to call it, active, passive, right? So it's more familiar to everyone. And then we just do a sync in the DB. So, but for Kafka, we do this thing. We can use tools called either Mirror Maker if you're on Community Kafka, or on Confluent, it's something called Confluent Replicator, right? So then what this does is essentially reading data from this cluster. Let me just put it here, right? And then copying that data across, right? So that you have one cluster constantly running, being the active, and then you copy things across, right? So this setup is very simple to understand. Similarly, this is active passive basically. So you have this cluster being the active, this one being the passive, right? So if you want to do active active, meaning I want to be able to produce both sides, right? It's doable also, right? So you can do it like that. But this means I also need another mirror maker or replicator, right, to copy data the other way. All right, so that's let me use the nice rounded. Right, so you need to copy from 1 to 2 and then from 2 back to 1 again. Right, so this is something that is also quite easy to understand, active, passive, active, active, right? So the issue with this, right, comes when, this guy is not going to be perfectly in sync, right? So notice that like before, your producers x equals to 1, this is one cluster, this is a separate cluster, right? So when I'm producing to this cluster, I really don't care that there's a replicator or mirror maker that is going to copy data across, right? Because to me, I only know about cluster 1, right? So that's the situation. So I produce, I get acknowledgements, and that acknowledgement is does not depend on whether that data has been copied across, right? So we are doing asynchronous replication, right? If you think about it, asynchronous, meaning that at any point in time, right? So with 2 DC clusters, I forgot to mention, we are now outside of the realm of single component failures. We can start tackling data center level failures, right? So in this particular case, this whole guy goes down catastrophically, right? Doesn't really matter. Doesn't hurt us because we have another cluster we can all shift to and copy, right? But there's one issue in this setup, meaning you have this thing, always this thing to worry about, which is your replication lag, right? So, and this alone is the biggest consideration that you will need to have around this, right? So if your connection is slow, or if your replicators or mirror maker instances cannot keep up with the high throughput, right? Let's say you're producing millions of messages every second, your replicator is 1 second behind, for example, then that's 1 million messages that's not here anymore, right? So then how do you proceed knowing that you have some missing messages in the DR cluster, right? So in this case, the passive or the secondary cluster is the DR cluster, right? So I cannot give you like better advice around this. It depends on your domain. Some folks will say I can monitor the replication back, so I know I can trace back which messages are not there. Then I can copy the messages across, manually, or have some other setup to pull from another database or all that stuff. Right? And that's well and good, right? So it's just additional considerations that you will need to make when you are doing this using Mirror Maker or Replicator for this replication. Right? So this is the primary consideration. Although it's pretty common, it's quite popular also when it comes to folks, setting things up. Just be mindful of the replication lag. And there's the second part, which I will just quickly run through, consumer offsets translation. I'll just put this here. If you're interested, there is a article somewhere that I need to find that is here. Right, it is a document called Disaster Recovery for Multi-Data Center Apache Kafka Deployments. Right, so I shall put the link here. I'm not sure how I can put the link here, but let's just go with it. 1 second. Maybe I just do. Okay, the link is here. For some reason, I cannot paste the text. But anyway, the search string is disaster recovery for multi-data center. I think once you get to the 5th thing, Google will pick it up and know that you are looking for this document, right? It's a free white paper, so just go ahead and get it. It talks about consumer offsets and how then we need to also consider how to perform that translation, all right? So that's one thing. Perfectly fine and good. In fact, there are a few, folks who are really into this type because it's easily understandable. I have a cluster here, I have a cluster there. I'm just copying data across. There's not too much complexity in the design, right? So that's how you go about doing that. All right. So that is the 2DC cluster replicator based, right? I'm trying to rush a bit because I have a small demo to show. So let's get to that. Okay, so there is another 2DC design. We call it the stretch cluster, right? Stretch meaning, I guess there's no meaning for stretch. So I'll just try to avoid explaining what that means. But basically you are stretching your cluster across 2 data centers. Essentially, that's what it's meaning. Right. So we forgo these guys. We treat this entire thing as one cluster. Right. So with Kafka, there's a few settings. There's only one setting essentially. You just need to set broker.rec. Right. So something like this. And this one would say broker.rec is equals to EC2, for example, right? So like that, you have a stretch cluster, right? So basically you're deploying them as one single cluster across 2 sites. And what this means is that when you set rec, broker.rec, you are enabling a feature in Kafka called rec awareness, right? Meaning when you then create a topic, right? In this case, right, when you are looking at 6 brokers in one cluster, so your replication factors recommendations will be different. I would say 4 and 3, right? So I'll explain a bit later why 4 and why 3, right? So later on we'll cover that. So that means, right, 4 replication factor, meaning you need 2 brokers from each data center, right? Basically, let me call it DC. So they are not separate clusters anymore. They are DCs. All right. So this DC1, DC2, you have 6 brokers. replication factor of 4 with red awareness. Kafka, when you create the topic, it will guarantee that you will place 2 in DC1 and 2 in DC2. So it could be maybe, for example, your leader is in broker 1, right? And then you have a follower maybe in broker 3, right? And then after that, you have 2 more followers in the second data center. So this spreads your replicas out, right? So why minimum in sync replicas of 3, right? Is so that when, let's say you have a message M1, right? So I get this all the time, especially when later on we'll talk about the failover and failback steps, right? There are additional considerations for that, and folks will try to change things around. Yeah. So we have minimum in sync replicas of 3 because you have the message going to the leader. You have the message, most likely the closest broker would be the one who gets the copy, right? But not guaranteed, right? Then you will have at least 1 copy of the message in this side, right? So that in any case, if this whole thing dies now, I'm guaranteed that from the producer's perspective, your message M1 exists across in the other DC. All right, so that's to force that type of relationship. All right, so then after this, then I'll acknowledge to the producer, right? So this is the 2DC stretch faster. So the first consideration for this whole thing, right? Network latency. I have a bridge. So if this thing is like a 56K modem, right, then I'm in trouble because then every single message that I produce needs to go across to the other DC, right? So that means that whatever latency this guy is, right, is going to manifest itself in my produce. So of course you can do other things like batching and all that to lower the performance hit, but this is still, you know, the recommendation is below 50 milliseconds, if not even less than that, right? So that will not be a major factor when it comes to your produce latency, right? So that's the main part. The second consideration is, right, if you are very into zookeepers and stuff, right, you'll realize that this is an even number of zookeepers, right? And zookeepers don't like to be in even numbers, right? So you are perfectly right in the sense that your zookeeper configuration has to be more interesting, right? Cannot be like that. So I will illustrate. So what our recommended approach for this, right, is to have zookeepers in a hierarchical quorum. All right, so meaning you set zookeeper groups. So later on, I will share some Docker Compose files in a repository. Then you can see what I mean and how it's being configured. All right, so that is group 1. And this guy is group 2. Right, so group meaning 3 of them have 1 vote. And 3 of these have 1 vote as well. So this is not meaning that I solve the problem when this guy dies and then I still have quorum, right? It's just meaning that I can then reconfigure this pretty quickly. I can configure this to be a single quorum, right? And then I don't need to, I can proceed as with this cluster, right? As per normal. All right. So that's the second part. And then the third thing, if you are really focused during this call, right, is you will realize that if this thing dies, then you will point to minimum in sync replicas and tell me where is there 3 over here, right? I cannot suddenly make broker 6 an in sync replica, right? So that's correct. So you'll see that this guy will be the leader, but my producers cannot produce into this cluster. Right? It will say not enough replicas. So later on, I have a demo I can show you. So there are steps involved, right, in terms of the failback, handling min in sync replicas. All right. So consideration is that, and then failover, failback steps, right? Is these two. All right. So you thankfully min in sync replicas is a reconfigurable config. So you can go in and say that I temporarily reduce it to 2, then my producers can continue producing into the cluster, right? So that's perfectly okay. Right, so there's a few steps involved, which I will guide you through later on. And there is a repository, if you're interested, it's under my name. I hope I can paste this link now. For some reason, it doesn't let me. What's going on with Lucid Chart? Okay, never mind. So you got, it's called Kafka DR Playground under my name, CHUAHJW. Yeah. Kafka DR Playground. Right, so if you're interested, you can clone that and then we can play along as we go ahead. Right, so we only have another 23 minutes. So let's move on. So then there is a 3DC stretch cluster design. So promise this is the last one. So we will not go to like 10 DC stretch clusters. So this is the limit. Everything else you will have to design yourself. Right, so let's go. Okay, let me copy the whole thing down. Sorry to kill your eyeballs. Give me a second while I get to it. 3DC stretch cluster. All right, meaning I have now a third DC, which is more exciting now. And then I don't have to keep that even number of zookeepers. Right, so in this setup, I can even go like, I know you can do 333 zookeepers, but you can do like much less if you want to, right? So it doesn't really matter. Okay, let me just delete all of these guys for now. I keep one set. So 1 to 9. In this case, you could even nuke all of these. You have just 3. Right? 1, 2, and 3. Right? Depending on how you want to do it. Right? All right. So my zookeepers, I have an even number, so most folks will not be complaining. So this will be fine. I can do 2 brokers each DC. As you will see in my example, I have 2 brokers each DC for a total of 6. So it doesn't mean you have to buy more machines to do a 3DC stretch, right? So it means you can spread things out across multiple data centers. All right. So how you would then structure this is you would have your replication factor at least to be 3, and min in sync replicas to be 2 once again, right? So meaning that I have the same topic partition, right? One leader, let's say for simplicity, broker 1. Because we have rack awareness, right? What happens is I have 3 broker.racks, like DC 1, 2, and 3. So your broker would then create the replicas. They will assign the replicas to the other 2 DC. So it will divide equally. Right. So one follower will be here, let's say broker 5, could be 4 or 6, and the next one is 7, for example. Right. So min in sync replicas of 2, again, back to the same game, right? So when I produce something, this will at least copy across to one other guy before I acknowledge, right? So that at any point in time, there's a failure, right? Then I have this guy would be the new leader. I still have 2, right? 1 and 2. Min in sync replicas are of 2. So I don't even have to bother about handling my min in sync replicas. My zookeeper, 2 out of 3 is still a majority, right? So I don't even need to handle the zookeeper configuration, right? So with this design, right, if your network latency is able to handle it, you essentially have automated failover and failback for a single DC failure scenario, right? So I don't even have to do anything. Except for maybe for your applications, if this guy is sitting in the same DC, you may need to move it around, or so that's something to take note of, right? So this is more common on cloud deployments, right? Whether you are deploying Kubernetes or directly on EC2 VMs or whatever Google calls their VMs, right? So you will typically have 3 AZs available. Then you can basically play around using this type of setup. So I see this a lot for cloud types of deployments. All right. So when one of the AZs goes down, your cluster is not impacted. So basically automated failover, failback. All right. There is a hybrid setup, right, to break this Zookeeper configuration portion where you have a third DC. Right? I promised that was the last one, but this one is important in the event that you are interested, right? So doesn't matter what broker, it doesn't have brokers here. So you can actually theoretically, sorry, let me just copy this out and delete this. Theoretically, right, to keep your even number of zookeepers, I can have like, I don't know, something like this, maybe. Bring to front. All right, 1, 2, 3, 4, 5. All right, so I have an odd number of zookeepers and everybody is happy now, because then what happens when my DC1 fails, right? I have 1, 2, 3 zookeepers, right? So I don't have to reconfigure zookeepers. I don't have to make it into some hierarchical quorum or something that's not too familiar with me, right? So I can just go ahead normal, right? But you still need to handle your main and sync replicas because 2 is less than 3, right? So that's how it's going to be. And this particular design is called the 2.5 PC stretch cluster. All right. There are designs, but that is Confluent platform only, right? Where you can support observer brokers and have them automatically promote themselves and all that other stuff, right? That also will, you can put them here. So you can also have pseudo automated failover, failback in a 2.5 DC setup, right? So the difference between this guy and the 3 DC, right, is that the third DC here is actually doing something. You need to place actual brokers on them, so they have to be pretty heavy. This guy is small. Zookeeper's requirements tiny. 1 CPU, 2 gig RAM. Typically that's it. Right? Brokers, we typically recommend 24 cores, 64 gig. Many terabytes and all that stuff. Right? So because you're storing real data. So this, we joke around, we say your third DC, your Zookeeper can be in a laptop on somebody's desk, but don't do that. This can be a small machine, basically. That's all I'm saying. Right. So these are the basic design patterns. I think today we've covered 1, 2 DC, 2 DC stretch, 2.5, right? And also the 3 DC stretch. So I will just quickly jump into the demo. This is not going to take too much time. So it's all in the playground. So if you're interested, just go ahead and run that Docker compose up. Right, so this will spin up a setup with 6 zookeepers and 6 brokers in the design in a stretch cluster. So the zookeepers, if you look into the Docker compose, are set up. Let me just briefly run you through that. Are set up according to, excuse me, yep, groups, right? Zookeeper groups and all that cool stuff. So I also have a failover one that I prepared, right? So in the original one, it's Zookeeper 1 to 6. In the failover, it's 1 to 3. Right? So there you have it. All right, so things are running. Let me take a quick look. All right, so everything is up. Let's start some stuff. Let's say Kafka, maybe not here. maybe back here. Topics. I have all of this set up, but I need to find it. Right, so I have a 2 DC stretch. All right, so 4 and 3. Replication factor 4, meaning string replicas 3. The name of the topic is test topic. All right. So let me just create that, and while that is happening, I will just play around with my windows. Right, created topic, test topic. All right, so then I can maybe watch this guy. I am describing my test topic. All right, so it takes some time. My computer is slow. Right, if you take a look closely, 1, 2, 3 are in DC1, 4, 5, 6 in DC2. Guaranteed you have 2 in DC1 and 2 in DC2. 1, 3, 4, 6, right? So 1, 2, 4, 6, 1, 2, 4, 5. Right? There's no situation where you have 1, 2, 3 or 4, 5, 6. All right, so that's the rack awareness in play here. All right, so I will do something interesting now. I am starting a producer performance test, but I'm limiting the throughput to 10 messages per second into my test topic. So you see what happens when we kill stuff, and what happens from the producer's perspective. All right. So this is just a constantly running producer. Likewise, I have the consumer that is going to just keep reading from consuming from this topic. Right? So it was just gonna, because perf test will just send the same string over and over again. Right? Then you have our watch here. So we'll go ahead and do a kill. Right? So let me kill. So I'm killing. No, not this. Sorry, this will be the next one. Broker 4. Right, brokers 4, 5, and 6, and zookeepers 4, 5, and 6. Right, so we are killing them, not shutting down. So you will see everything is in bad shape, right? So remember, we have to do 2 things. One is zookeeper reconfiguration. The next one is to fix the main string replicas, right? So you will also notice that this guy has hung, right? This was supposed to run every 2 seconds, but now it's already 7:48. It's not running, right? Because you don't have zookeeper quorum. We cannot fetch the metadata. We cannot fetch the topic, information at all. Right, so nothing is working. All 3 screens are practically dead. Right. So first and foremost, reconfigure zookeeper. So I will up the failover. Right. So all this does, right, is reconfigure zookeepers 1, 2, and 3 in a single quorum. Right. So then you will realize that what happens next is that you have your admin client back, which is basically you're able to describe the topics. Then your producer side will have a different complaint because now there will be a new leader. Then it will just say not enough replicas. So give it some time to, right. So as I said, not enough replicas, right. So now it's not that I cannot find the broker. Now it's I found the leader. I'm trying to produce to it, but there's not enough replicas because main instinct replicas you told me is 3, right? So now there's only 2. If you look at this, 2 in sync replicas. All right, 2 of them are offline. So remember the second step we needed to do. One is to fix the, so basically fix the main insync replicas config. So one way of doing it, you can do like Kafka configs, right? So I'm going to do this for the consumer offsets because the tool that I'm going to talk about next doesn't touch the internal topics. Right? So for consumer offsets, I'm going to set it to main insync replicas of 2. This allows then your consumer to commit offsets. Right? So now it's saying offset commit failed. Right? So give it some time. Okay, coordinator is not available. Okay, maybe later on you will decide to wake up. All right, so that's that, right? Then the next thing you can, we need to do this for every topic, right? So if it's a bit troublesome, there is a tool called Kafka failover CLI. Sample tool, not production ready, is written by some of my very senior colleagues. So sample, you can use this to build whatever you want out of it, right? So it says you run that jar. My bootstrap server is this guy. C meaning currently everything that's set to 3. I want to set to 2, right? So this meaning I capture everything except for internal topics. So then I would run it again, right? So this goes in and reconfigures the min and sync replicas for everything. All right. So then it basically fixes your problem. You now can produce messages again, and consume is no problem. Just now I think it was fine. It was just the last message was coordinator not found, then it's found, and it just no messages, right? So that's all there is to it. So then what happens next, right, is when everything comes back up. So that was the failover. Now I'm running in single cluster, single DC mode, right? So then what happens when everything comes back up again? Right, so then I up everything back to what it was before. Then we wait, right? We give it some time. All right. Sorry, I'm just sending the links to Teck Chun, and you can broadcast. Yeah, thanks, man. All right, so it shows offline and all that stuff, right? So while things are spinning up, let's hope nothing dies. All right. So you saw now broker 5 and 6 are not in the offline mode, offline list, but no, broker 6 is not in the offline list, but they are not in the in-sync replicas. Means they are still catching up, right? So they are not offline, but they are still catching up. All right, so everything came up. So give it some time, it will eventually catch up, and you will see 4 and 6 in the ISR list. All right, so at this point in time, you are back to running 2 DC mode, right? So that's when everybody just, we averted a disaster, let's go on holiday, right? But the problem here now is, right, you realize that your min and sync replicas is still set to 2, right? So it's very important for the failover step that you also reconfigure it back to 3, all right? So then that means we do this guy, set it from 2 to 3, and then this guy from 2 back to 3. All right. Doesn't affect anything, right? They're still running. They're still happy. We still have 3 in sync replicas, so it's fine. So, but this is the step that we need to remember. Right? Otherwise, you are running min in sync replicas 2. Right? There's a possibility of future failure on one of the DCs. You will lose data. All right. So that's that. So in the interest of time, I will quickly jump to the next one very quickly. That one will be pretty, not much to, oh, sorry, wrong thing. Docker compose down. Right, so you can try it out yourself, right? When you, when you clone that repository, you can take a look at how things go. 3DC stretch. This one would be most straightforward. Right, 3 zookeepers and 6 brokers. Right, so 2 in each data center. So that's what I'm doing. Yeah, these 2 you can ignore. Technically, you only need the zookeepers and brokers. So I will create, and I will do replication factor of 3 min and sync replicas of 2. Yeah, take some time for everything to spinning everything up very slowly. Okay, so let's get into a segment on awkward silence. Okay, great. It's up. Sorry about that. My computer is very slow. It's not the latest flashy MacBook. So I'll try to get one procured. All right, so you have three replicas, right? Same thing, right? You have one brokers 1 and 2 are in DC1, 3, 4 is DC2, 5, 6 DC3. So you will never see 1 and 2 in the same list, right? 3 and 4 as well, 5 and 6 as well. So it's spread out. You will have replicas across all your DCs. All right, so that's the main thing. And over here, we can do exactly the same thing and exactly the same thing. So hopefully it's gonna run. All right, producer, consumer running, client running. Everything is updating. Although it's not every 2 seconds, I think it's a bit slower. I think my computer is not doing very well. Yep. All right, so it's updating. So you can start to kill stuff. So let's say broker 3. Let's say I killed DC2, right? What will happen is that broker 3 used to be in DC2, right? So it was the leader for partition 0. So now it's complaining that cannot be found. So my producer is saying I cannot find this guy. So I will have to move on with life. So but after some time, again, right, your leader will be reassigned. In this case, to leader will become broker number 6. It says I'm taking over the leadership. So the producer is able to find it and it's still proceeding on with the produce and consume. Right. So notice I haven't done any configuration, any starting of anything else. I didn't reconfigure minusing replicas and all that. Right. So it just by itself, so that's why we call it automated failover failback with some if you're interested in the RTOs and all that, right? So a few seconds, not up to a minute, right, of RTO as the cluster figures out who is the new leader and all that stuff, right? So that's this is the 3DC stretch cluster, all right? So that's fun stuff. Admin client, because I have 2 out of 3 zookeepers, it's still a majority, so everything is happy. All right. So we have to schedule some time for questions. Sorry about that. This took a bit longer than expected. So I will stop sharing. So once again, the repository is there. If you are interested, there's, quite, I will try to update it when I add new stuff to it. Yeah. So back to you, Teck Chun.
All right, thank you, Jinwei. Thank you for the very detailed step-by-step explanation, diagrams, and also demo. Right, I think we learned a lot today. Yeah.
Sorry for that. Before I go, this is
Yeah.
so sorry. I nearly forgot. Anna, can you share my screen? If you can
okay.
share
Yeah,
my
sure.
screen back again. Sorry. Yeah,
Yeah.
I am so sorry. Yes, I promise, Anna,
Oh,
my colleague, that I'm going to splash this screen. So if you are interested, right, Confluent developer site, developer.confluent.io, a lot of examples you can run there from the application development side. And please join our Kafka user group, cnfl.io/community. Yeah, sorry about that, Teck-Chun. Yeah, back to you.
no problem. Great. Yeah, you want to post your link that you talked about just now, your GitHub link and your other links on the
I posted
private chat.
in the, yes, I
Okay,
just
can.
did, yes.
All right. Thanks for that. Okay, I'll post it to the channel. Oh, okay.
Yep,
All right.
thank
Thank
you,
you.
thank you.
Thank you. Let's take a short bio break, 5 minutes, and then we'll be back for the second speaker. I don't see any questions to it, so thank you, Jinwei. Hope to see you back
Hey,
again for the
thanks.
next one. Right.
Hey,
Okay.
no worries. Thanks a lot, man. Thanks.
Okay. Okay, guys, we'll be back in 5 minutes. See you later. All right, welcome back. We are back from the break of 5 minutes. And next speaker, we have Donald. And on the screen, we have Ravindra, who is also the co organizer of this meetup group. You want to say something? Hello, Ravindra? I think you're on mute.
I'm very excited to be part of this community, and let's see how we can scale up the community as bigger as possible. And hopefully, this is gonna give a lot of a driver for a lot of learning for the people from the data background as well as those who wanted to move towards the data. So, thank you. That's all.
Okay, thanks, Ravindra. Yeah. Okay, next up we have Donald. Donald is an engineer from DataSpark and also my company and Ravindra's company. And he will talk about Airflow today. So over to you, Donald. Let me put on your screen first. And here we go. Hold on,
All
give me a
right.
slide. Hold on.
Yep.
Hey, over to you, Donald.
Okay, thank you, TC. Yep. Good evening, everyone. I'm Donald. Today I'm going to give you an introduction on Apache Airflow and how to power it up with variables and API using the dynamic DEC generator. Today's presentation will be broken down into two parts. The first part will be a very brief introduction on Apache Airflow to get starters onboarded. On the second part, we'll be covering some problems which I've identified when working with Airflow and the hacks that I did to create dynamic DECs with variables and generating DECs with a DEC generator too. But first, some background about myself. I'm a data engineer from DataSpark. Before joining DataSpark, I was working as a project consultant in an ERP software company where I have direct contact with business owners to understand their pain points and to solution for them. After a few years in this field, I realized that the traditional software engineering approach might not be suffice for solving all problems. After much research, I was exposed to on how to better use data in solving problems. Subsequently, I spearheaded the usage of data analytics tools and exposed my company to a more data-driven approach. As I continued to dive deeper, I was awed by the power of data. And so I left my roles to take on a master's in NUS, specialized in analytics, sensing systems, and natural language processing. Somehow I found out that I fell in love with working with data. So I decided to pair myself up in a workplace where I can work with endless streams of big data. That's why I'm here today at DataSpark as a data engineer, where I get to play huge amounts of data with the most cutting edge technology. Okay, some intro about DataSpark. DataSpark is a company which provides powerful insights and advanced analytics capabilities to businesses, government agencies, and telecommunication companies. That's why I'm here. We are the leader of creating and applying population-wide mobility insights to address social economics and business problems in the most innovative ways. Here's some case study that we did. So what we do in DataSpark, we work and play with big data. We solve new problems every day. We get exposed internationally, given our presence across the region. We get to meet the most amazing and talented people supporting growth and learning. We take real ownership over everything we do. And we get to explore cutting edge data science and engineering technologies. Before diving into today's topic on Airflow, I will start with some challenges in working with traditional shell scripts. It's always a sequential process where there's no parallelism in the computation. There's no information about like the dependency of each task other than the sequential operation existing in the script. We need to rerun every time any parts of the modules fail. We need to rerun the whole pipeline. There's lack of compute visibility, and we are often blinded from the progress of the pipeline. Therefore, it's very difficult for us to debug where we don't actually understand or know where the issue lies. So let's start off with this. On a typical work day, I usually have a dilemma in the morning to stay longer in bed or to make my breakfast. So I have an idea of making Airflow automate my cooking so I can stay longer in bed while my robots help me prepare my breakfast. I'm going to use this as an example to give you a quick introduction on what Airflow is and how it works. First, to get information on the overall process, I will need to Google for a recipe for my breakfast. And today, a sunny side up. Then I'll capture the actions required and define it in the codes. Something like medium heat on pan, so some oil, crack eggs into pan, and blah, blah, blah. Subsequently, I'll define the flow of each action. Once done, I'll save this Python script and place it in the Airflow folder. Then we can run it on Airflow and be one step closer to an effortless breakfast. Special note to these two tasks side by side. These tasks are done parallelly. Oh wait, okay, I have some interchangeable ingredients that I can use for this recipe, so I don't have to be stuck with the same flavor of eggs every day. So I went on to define the interchangeable ingredients in my codes. In this case, the type of oil I can use in my eggs. So in the future, I wouldn't have to modify my code base to change the ingredients to make my eggs. So ta-da! Once completed, my new egg is going to be cooked in bacon oil. However, Airflow is required to connect to my robot to get codes into action. So I will have to set up some connections to get real work done. I can show you how is it possible to actually chat on the robot while I'm still lying on my bed. So Airflow provides a very intuitive user interface to describe how each task is doing. We can see like live and historical status of the whole process. As you can see, all the status are of different color codings, whether it's successful, running, failed. In this case, the robot has failed to crack some eggs in my pan, which causes the rest of the downstream to immediately stop. Airflow also has some graph to show you how much time each task takes, the total attempts for each task, and a Gantt chart to display the start and finish time of each task. We can also configure it to like send notifications on failure or once it's completed. So I can get notified to get out of bed for my breakfast. There are also logs that can be accessed from the UI to check what's going on and understand what's the process that failed and what's actually failing. So it looks like I've run out of some eggs. Yeah. Once I have topped up my eggs, I can resume from where it failed, and I don't have to run it again. Airflow can be useful for handling complex tasks. For example, making some Scotch eggs when I'm sick of sunny side up. When the task gets too complex, I can group tasks together to have an abstract on how the groups and tasks are running. I can also explode each grouping to actually have a micro view on the task. Airflow is also API enabled, so it enables us to use API calls to get information such as the status of the deck, run some decks, inject some new variables, get a list of task instances, and more. It also has good support of operators to help you fulfill your tasks, from email operators, Hive operators, Druid, and Python operators. There's also a huge community support, and here are some of the most popular integrations in the community. So as a recap on how Airflow can help you orchestrate your pipeline. It's easy to understand the workflow as you can neatly group tasks together of the same category together. So it allows you to configure tasks with variables without editing any of the code base. It enables processes to be run parallelly and offers connections to other interface and other platforms. It provides status notifications as required. It also provides detailed logs on each task of whether it fails or on successes. It allows you to recover a pipeline without restarting the whole entire process. And it has API built in for remote tracking and deck operations. Here's part 2, where I'll be sharing with you the problems that I identified when working on Airflow And what approach I've took to solve these problems. Challenge number one, I feel that it's like not very self-serve. Engineers need to know Python and Airflow in order to create a pipeline on Airflow. It requires a Python script in order to get a deck built. It requires a lot of duplication of codes, especially when you're using the same operators. Housekeeping is rather tedious, as you need to locate and remove the Python file that you don't want from the deck folder. If tasks can leverage on variables, can it be actually applicable for decks? So in the coding world, I deem nothing impossible until I have tried. So I decided to work on a prototype to prove the concept. I started off with abstracting all the information required on the decks, for the decks in the JSON format. For example, the important information like deck name, description, probably time schedule, and also the start time of this deck into like JSON format here on the right. Similarly for all the operators and the flow. So I managed to use a few lines of codes to allow Airflow to actually extract the key value pairs from variables on the fly. So this piece of code actually queries the session to get get the information from the variables. Subsequently, I'll need to extract the information to fill the constructors of the decks and operators. Some string manipulation has to be done to fill in all this information to the constructors. So to execute the flow is much more simpler than to initialize this flow. Some text manipulation has been done to change the list type to string. I use Python to execute method to execute the string, which is dynamic on each call. So if I have like different kind of flow, like task 1, task 2, task 3, maybe sometimes it will be some other strings that I need to use. So this execute will be able to handle this kind of like dynamic flow that I want to actually initialize. So by combining all the previous, what I've done on the previous few slides, I've successfully created decks using variables. I'll be covering this on the end of this presentation during a demo. Here are some advantages of deck creation from variables. Number one, like we are able to create decks without prior knowledge in Python and Airflow. No coding is required. Duplicative codes are eliminated. It opens up possibility of creating deck with just an API call. It reduces time spent onboarding new teams to Airflow. It makes housekeeping easy as decks will automatically be removed once the variables are non-existent. So let's go on to problem 2. Imagine your PM giving you a new pipeline to build. It will always feel like building a 30,000 puzzle piece. Even worse when they ask you if you can complete in a week. So why is it difficult? Like I mentioned earlier, building Airflow pipeline is just like completing a set of puzzle. We need to understand the requirements and the dependency in order to map it properly. Errors are very common when we try to wire it up manually, and it takes some trial and error when it doesn't work. So if a single task in a pipeline may take hours or days to run, in such cases, troubleshooting might take more than a week. I guess in the end, your project manager wouldn't be happy about it. So in order to solve the puzzle, we know that each puzzle piece has knobs and holes. using these facts or evidence, you can actually transform it into what we can identify in tasks. Every task has its own inputs, dependency, and also the outputs. So given this information, right, I map all this information in JSON format with the required arguments for running a task. Using a simple Python tools like Network X to map out each vertices and edges of the task, so I can get the relationship between each task. I use Streamlit to create the UI and some the Plotly library to visualize, to allow visualization on the graph for users to understand the relationship between each nodes and their dependencies. So this is the result of combining the tools. On the left, you can see a screenshot of the tool I created called the pipeline generator. At the start, the tool generates a default pipeline of one of our products. It also offers visualization, providing information of the whole pipeline. When you hover across a single node, it displays the task predecessors, inputs, and outputs. After providing the DEG name at the bottom, it allows you to do an API call directly to push the variables to Airflow to get the pipeline built. So the generator is further improved to allow users to select the start point and the end point to create their own subset of pipeline. So for example, just now I show you the full pipeline, which is very complex. Now we can almost break it down into little pieces from whichever desired start point to the end point. For example, we have a set of tasks A to F, as shown here. We only want to output the output from D. We can easily determine the path required and eliminate the non-essential tasks quickly with a pipeline generator. So the advantages of generating a DEG is that we don't need to do manual mapping. We just need to base it on the inputs and outputs of the task. And it provides easy visualization of like the task dependency and mappings to new users. It creates a pipeline or a subset of tasks quickly. It provides seamless integration using API to create DEGs via variables. So I'll go ahead with a demo on what I've done for the DEG generator. So let's do a refresh here to make sure everything is running properly. So this is on the left is the interface of Airflow. Currently, we have two DEGs here, 120 sample C, sunny side up breakfast. This is what I use to make my breakfast. So we have this admin tab here, which is the variables, which I set. I can configure, I can generate a DEG and import into variables for DEGs to be created. And I can create like connection variables here. I will not cover everything in details. I will just cover the works that I've done to generate a pipeline using the DEG generator. So if I go into variables, you can see there are a few initialized variables here. Basically, how the whole Airflow, I mean, how my works actually takes in the variables is as such. We have a main DEG variables here, which I call the 120. It has the DEG name and all the required information required to build a DEG. Subsequently, it will have a flow variables at the bottom, which points to the reference flow that I want to generate. So this 120 flow will link up with the 120 flow, which is described on the second variable here. So for each task, for each flow, we'll have a functional group. It groups all the mini tasks into groups. Then it has all the different tasks within a group and all the different variables that's required for the pipe. I mean, for the, let's say if you have a jar file, the arguments that is required for the jar file to run. So I'll go on to the, okay, I missed out something. Lastly, I have this flow. Let me just go into the record. Lastly, I have, for each groups, I have a flow which describes how two tasks are actually associated with each other. So we can say that at-home congestion is upstream of hourly congestion, and so on and so forth. So within a group, there will be a flow, and at the outside layer, we will have another flow to control how each group is related to each other. So this is the complexity that we can do with a pipeline generator. So let's move on to the pipeline generator. On the right is the pipeline generator. So we have a start point and also the required output. Like I said earlier, the required output is at start is basically all the outputs available in the pipeline. So it creates a flow chart like this. So as we hover across different nodes, we get to see what are the predecessors, inputs, and outputs of each task. If we scroll over like the lines, we get to see like how is it connected to to the next task. After which, if you want to generate a whole pipeline, we just need to enter the DEC name. Sample DEC. We need to configure the connections. Let me just quickly get the connections. I'll paste my Airflow IP here, and I'll post that. It'll take some time because I'm also not using the latest M1 Mac. So yeah. Okay, once it's successful, you'll return a successful value. So we need to first check whether the DECs, the variables are actually created. So I named the DEC name as sample DEC. So as I scroll down, okay, why not I just do a filter here. Yep. So we can see that the whole pipeline is actually created here with the flow variable here. So let's go to the main page and check whether the DEC is created. Yep, the DEC is created here on the main page. So if we access it, it will look similarly to the one on the right. Yep. So this is the whole flow, and there are mini tasks encapsulated inside one group. Okay, so let's go on to creating a subset of pipeline. So we can just simply select any start point. Let's say, I will say I want to create from something like, maybe not from the start. Demand or something like oops, sorry. To maybe a so upon entering the required outputs, it generates a flow chart. This flow chart is shown from top to bottom. I didn't cover that just now, but it's from top to bottom. So we can see actually the information flowing from the top here. The first node will be forecast current usage runner, and to the last process name, which is called the metric predictor runner. So I can do it again. Subset of pipeline. With this, oops. Let me just try again. Yeah, with this, we have successfully posted the DAG to Airflow. Let's check it out again. Okay, maybe it takes some time to load because I'm hosting all this on a single computer, so might take some time for it to register. Let me check on the variables first. Yep, subset of pipeline is here, and the subset of pipeline flow is here. Okay, yeah, finally it appeared. So yeah, this is how we can actually use graphing tool to actually help in creating a dynamic deck through variables in Airflow. Yep. So I'll go back to my slides. Any questions? Any questions from the floor?
All right, thank you, Donald. Yeah, don't see any questions from online. Okay, great. Where can the viewers find more information about this deck generator, Donald? Is there something that you have?
It's not public at the moment, but I think I am able to share, but yeah, just give me some time. Probably I'll just post some links for some reference. Yeah.
Okay, okay. All right, good. Thanks for that. Let's wait a while to see if there's any questions. All right. All right, no. Okay, great. Let me put back all the speakers today and also organizers. Yeah, I hope Jiwei, are you still there?
Hey, yes, sir, I'm still here.
Okay. All right. I think thank you very much for staying through, and for those online viewers, thank you also for staying throughout the evening for our first meetup. There will be more to come over next year. So we also wish to hear what topics you want to know. We'll start something in the meetup group and post it, and you can give us your feedback. Okay.
Sorry, I have two
Also,
more
feel free to
slides.
reach out to-
So sorry to cut you. Yep. Can I do that?
Yeah, sorry. Go ahead. Yeah.
Yeah, if you want to know more, please scan this QR code to find my LinkedIn and email.
Okay,
Yeah.
let me share the screen. Hold on. And here we go. Let me share the screen.
Yeah. Thank you, TC.
It's a bit of a lag. Huh?
Yeah.
Okay.
Okay, please scan the
Okay.
QR code
Nice.
here to link me up on LinkedIn or email if you have
Right.
any
Right.
inquiries about this session. So thank you very
Okay.
much. Hope everyone has a
Yeah.
good Christmas and
Yeah.
New Year. Yep.
Okay.
And also some promotion on like the careers in data spark. If you are as passionate as me and you want to do more, yeah, please yeah, we are actually hiring data engineers and DevOps engineers here in data spark. Yep.
Yeah.
Back to you.
Yeah. And also data scientists. Yeah. Just to add.
Yep.
Okay. All right. Thank you. All right, then I think let's end here today. Thank you for all the speakers again, and have a great evening to everyone online. And we'll see you soon in January 2022. And have a good festive season ahead, and stay safe. So good night, goodbye.
Bye.
Hey, thanks, man. Thanks. Yeah. Cheers.
Thank you.
Bye.
Bye bye.